The final optimization of the design is varying the number of ribs. The ribs help to reduce the unsupported length of the hemisphere so it can be thin-walled without having too much displacement. Because the hemisphere is stronger at the ribs, it keeps the total displacement in check. But how do we know if 6 ribs are enough or can use fewer than 6? Varying the number of ribs is done by exiting the stress analysis and editing the component pattern containing the ribs. For this design iteration, the number of ribs is changed from 6 to 4. The file is saved and updated. The simulation is run again. Depending on your computer, this may take a few minutes to complete. The stress values have changed from 175 MPa to 257 MPa. The displacement has changed to 0.04095 millimeters, and the minimum safety factor has changed from 1.58 to 1.07. Comparing these results shows that the new design parameters do not meet the design criteria, and we've gone too far in our effort to lightweight. The stress and safety factor values exceed the design criteria provided. In conclusion, the design criteria of 12 mm wall thickness, 160 mm end cap height, and 6 ribs is the preferred design. This design reduced the mass of the assembly from 295 kilograms to 231 kilograms. This saves 64 kilograms of steel per end cap and is a 22% reduction. But you don't need to stop here. There are ways to make this part even better. As a challenge exercise, try and refine the design even further. Possible modifications include reducing the end cap wall thickness, using 5 ribs instead of 6, changing the shape of the ribs, or even lightweighting the bearing box. Throughout this simulation, we modified a number of parameters. Parametric studies allow you to nominate parameters for evaluation, define the parameter range, specify the design constraints, and analyze the results of each parameter variation. A parametric optimization can help you triangulate on the optimal geometry based on several variables at once. A video of a parametric study on the USS NCAP is provided for your reference. This preview of the video shows how you can use 3 values of the thickness parameter to determine the best solution. Note how the safety factor is displayed in red when the wall thickness is set below 15 millimeters. And remember, this simulation is based only on existing solar array designs. Using whole systems thinking, there may be a way to reduce the amount of wind loads that these drives experience in the first place.